We're going to be talking about the last kind of bit of Unit 9, which is all about polar graphs. So we're going to start with what polar is, go into differentiating it, and then integrating it and finding those areas. So polar coordinates or a polar plane system is a system of concentric circles, such as circles where the center of each circle is 0, 0. It's called the pole. We can do coordinates just like what we do with our Cartesian plane, x, y, except for our points consist of a radius and an angle. So if we look at these, we're going to be reminding ourselves that our points are a radius and an angle. So this first one, 3, 0, is a radius of 3 and an angle of 0, so it doesn't move. So when we talk about a radius, a positive radius means we're going to be moving to the right. A negative radius means we're moving to the left. So if I have a radius of 3 and it's positive, I'm going to start at 0, 0, and then I'm going to go 3 units in this direction. So if I look here, here's 2, 3 is going to be here. So a radius of 3 is right here, and if I needed to move this around our circle, this would be our angle. But because it's 3, 0, that's where we're at. Our second one is negative 3, 0. So negative 3, 0 means we were going to be, the radius is in the negative direction, so we're going to move 3 in the negative direction, 1, 2, 3, and then we're moving 0 degrees from that point. So our point B is going to be right here, which gives us negative 3, 0. 3 pi, so I go out 3, so I'm at point A, but now I need to, on the circle, rotate pi radians. So I'm going to go all the way around to the other side, and it's going to land right where negative 3, 0 is. So one of the things that you may notice is that when we write polar coordinates, there's a lot of different ways to write the same exact coordinate. The next one that we are going to do, 2 pi over 4. So we're looking at a radius of 2, so we're on this circle right here. And then going from the positive direction, I now need to go pi over 4. Pi over 4 is going to be right in that middle part. It's at 45 degrees angles. 45-degree angle, so I'm going to be looking at a point right here. And then our last one, E is 4 and then negative pi over 4. So 4, we're on that circle of 4. And then we want to go negative pi over 4, so in the negative angle direction, which is going to be this direction, but we still go pi over 4. So we're going to be right here. Normally I would have you guys make up your origin coordinate and then have someone else write the coordinate that you did, but we're not going to do that for this time. The next thing that we need to know is that if I were to take away the circles, these would look like a Cartesian plane. And we've kind of looked at the Cartesian plane and the polar plane at the same time. You guys just didn't know it yet. And the main way that we look at that at the same time is the unit circle. So we generally have a right triangle that gives us our x and y coordinate, but we also have a radius with a theta. So we can actually use that to help us figure out our x and y. So if I were to find the sine and cosine of these two things, sine is the opposite divided by the hypotenuse. Our opposite of our angle theta is y over our hypotenuse r. For x, we're going to be dealing with cosine. Cosine of theta is the adjacent over the hypotenuse, so x over r. And we can move these around so that way they're in that Cartesian format. So if I want to get y by itself, I'm going to multiply both sides by r. We get r times sine of theta. And same thing with x, we multiply both sides by r to get r cosine theta. So x equals r cosine theta, y equals r sine theta are the Cartesian format for our polar functions. So we can kind of go back and forward, but what that means is that we can take a polar curve and write it as a parametric function. So the first thing that we're going to do is we are going to rewrite we're going to rewrite this polar into parametric form. So the thing about a polar curve is that when I look at this, our radius is equal to 17 sine of 5 theta. This is our function. This isn't just the function for y, this is r in general. So when we look at our x equals r cosine theta and y equals r sine theta, we're literally going to take this equation, multiply it by cosine, that's our x, multiply it by sine, that's our y. So we have x is equal to r cosine theta, so we have r, which is 17 sine of 5 theta, and then we multiply it by cosine theta. So all of this right here is r. We do the same thing for y. So we have 17 sine of 5 theta times sine theta. All of this is r. So this would be our parametric format for those functions. So we can take any form of parametric equation or any form of polar equation and kind of change it back and forth between these two things. The big thing with taking a parametric and turning it into a polar is we want that sine or cosine there, so we can see, hey, this is r, this is the rest of our function. So we're really going to be using this to go from polar to parametric, so that way we can take derivatives and in that same form that we would a parametric equation.